This is our final video on chemical bonding and nomenclature. This will conclude the PowerPoint. Let's talk about how those dot structures for molecules were drawn. The chemical formula is going to assist you with the structure. The central atom is going to be the element that you have the least amount of in the chemical formula. So in these examples, we have 1 carbon and 4 H's, so C would be the central element. In NH3, we have 1 N and 3 H's, so N would go in the center. And in SiCl4, we have 1 Si and 4 Cl's, so Si would go in the center. Another helpful hint with these is that the number of single dots on the central atom tells you the number of bonds an atom can form. For example, if we draw out CH4, okay, carbon is in group 4A, so it gets 4 dots. 1, 2, 3, 4. Therefore, it can make 4 bonds with the provided 4 H's. Each H has 1 dot, because it has 1 valence electron. And that would be the dot structure for CH4. What you really want to do as you're drawing these is you always want to start by counting the total number of valence electrons that you should have in your formula. And then that should equal our total number of dots. In addition, for bonds, instead of 2 dots, we can use lines. We'll do an example. So for example, if we go back to the F2, okay, F is in group 7, so it has 7 dots, or 7 valence electrons, and there are 2 of them. So 7 times 2 equals 14. I'm going to draw my first F, draw its 7 dots. Then I'm going to draw in my second F and connect it to my first F. So here's one of its dots, 2, 3, 4. I now skip that location because I already have 2 dots, 5, 6, 7. What you'll notice in my structure is that each F is now in contact with 8 dots, like it's supposed to be. The other way we could have drawn this is like this. Notice that I've replaced the 2 dots in the middle with a line. Let's move on and do a couple of additional practice problems. Cl2 is going to look very similar to the F2 that we just did on the previous slide. So Cl has 7 dots, because it's in group 7, and there's 2 of them, so I'm going to need a total of 14. Draw my Cl, draw its dots, connect my other Cl, there's its first dot, second, third, fourth, fifth, sixth, and 7th. And then if I go through and count them, I'll see that I have a total of 14 dots. H2O is our next example. We have less O's than H's, so O goes in the middle. O has 6 dots. Each H has 1 times 2. So when we add them together, we get a total of 8. So I'm going to just bring my H's in, like so, to complete oxygen's octet, as well as make H happy because it only wants a total of 2 dots. Third example here, PBr3, P is going to go in the middle. I'm going to fill its octet, and I'm going to put my BRs around it. Whoops, calibration's off right there in that location of the board. Let's try again. I'm going to connect my BRs. My BRs are also going to have a full octet. The dots, there are a lot of them, I know. Okay, and then I'm going to see if I have the right number of dots in my structure. P is supposed to have 5. BR is 7 times 3. When I add those together, I get 26. I count my dots, and as I do that, I see that there are a total of 26 dots in my structure, so I must be correct. Carbon dioxide. Carbon has 4. Oxygen has 6 times 2 for a total of 16. So we're going to draw our carbon and fill its octet. And then I'm going to draw my oxygens and fill their octets. And I'm going to notice that when I count up my dots, right now, I have 20, which is not correct. So what I do when that happens is I start to form either double or triple bonds. So I'm going to remove these 2 dots here and these 2 here, and instead make it a double bond. I'm going to recount my numbers. Now I'm at 18. Again, I have too many. So I'm going to remove some more dots, 2 from the O and 2 from the C, and I'm going to move them to the middle. And when you count up your dots, you'll notice you now have 16 like you're supposed to. Okay? And everybody's happy. The oxygen is in contact with a total of 8, the carbon is in contact with a total of 8, and the other oxygen is in contact with a total of 8. So that molecule is complete. We don't really spend a lot of time doing ions, but I do want to do one example. Okay. Sulfur has 6. Each oxygen has 6 times 4. When we add those together, we get 30. But this -2 charge means we have an additional 2 electrons for a total of 32. So I'm going to put my S in the middle. Okay. I'm going to use lines this time, so I'm going to connect the S to all the O's. And then I'm going to fill the octets on the O's. So O has the 2 dots because of the line, so it needs 6 more. When I count up my dots, I end up seeing that I have a total of 32, because remember each line is 2, and that's exactly how many I want. Because this is an ion, we also often put it in brackets, and we put its charge on the outside. Our major focus is going to be molecules that are neutral, not ions, in the class. Let's move on. You'll get a chance to try some drawings towards the end of the PowerPoint. Let's talk about the geometry or the molecular shape of molecules. Okay. The theory that is used for this is the VSEPR theory, or the VSEPR theory. It's an acronym. It stands for valence, shell, electron, pair, repulsion. Okay. It helps us to predict the geometry of molecules as well as their bond angles. This is based on a couple of things. Okay, really, what the name says is exactly what it is. Okay. So these are going to be based on the bonded pairs. So how many things are bonded to the center? In addition to the lone pairs, or pairs of electrons that are just by themselves that are on the center. We're going to do some examples. The theory states that the valence shell, which is our outermost electrons, okay, have an electron pair repulsion. So they basically want to be as far apart from one another as possible. In this class, we're only going to focus on about 5 shapes, but if you do have to take the higher level classes, we cover a lot more. Let's move on and complete a chart together. So these are the 5 shapes that you guys are responsible for. You're going to want to memorize them and be able to identify them for your test. The bonded electron pairs and the lone electron pairs refer only to the central atom. Only on the central atom are we focused. When something is linear, it's going to have 2 things bonded and 0 lone pairs. The diagram kind of looks like a line. So we'll have our central atom and then 2 things connected. A good example is CO2, okay, which we drew a couple slides ago. In addition, something to take note of, if there's only a total of 2 things, so there's only 2 atoms, the substance has to be linear. For example, HCl. Okay, HCl is linear because there's only 2 atoms, so the only shape that it could be is linear. Bent is also sometimes called V-shaped. it has two things bonded to the center and two lone pairs. So the diagram is going to look like this. Okay. And then we put the electrons up here. Electrons that are free take up more space than atoms. And a good example of this is water, which we drew a few slides ago. Our next shape is trigonal planar. Three things bonded, no lone pairs, so it kind of looks like a flat triangle, hence the name. And a good example here would be something like BF3. The fourth shape is trigonal pyramidal. Three things bonded, one lone pair, and it looks kind of like this. It's like a tripod. And then it has a lone pair on top. Ammonia is a good example of this. Okay. Or from our previous slide, the PBr3 was a good example as well. And finally, tetrahedral has four things bonded and no lone pairs, and it looks kind of like this. So it's a tripod with a top, and CH4 is a good example here. The best way to determine the molecular shape is to first draw the dot structure, and then use that dot structure and what's around the center, as well as these numbers here for bonded and lone pairs, to determine which shape you have. Since my pictures are not very good, I know that, sorry. Here's another diagram of all of the different shapes, including the ones that you're responsible for. Your textbook also has some great pictures as well. The final thing we need to talk about in this unit, within this chapter, is the polarity of molecules. Okay. I'm going to write the definition now. Polarity is often defined as something that has a positive and a negative end, or as a dipole, meaning it has two poles, kind of like a battery. To determine the polarity of molecules, one of two things must be true, or both, potentially, but at least one. They either have to have lone pairs on the center, so the two shapes bent and trigonal pyramidal are always polar, or they have to have different atoms around the center, as in this example, the SiH3Br. If they are different, they are polar. If they are the same, they are what we call nonpolar. So we discussed that at the very, very beginning of the chapter as well. What I would like you to do is I would like you to pause the video, and I would like you to draw the dot structure, identify the shape, and the polarity of the molecules on this slide. The answers are provided. You needed to draw the dot structure first to then determine the shape and polarity. HF would look like this. Since it's only two elements, it has to be linear, but because they are different, it has to be polar. OF2 has two lone pairs right here and right here along the center, and two atoms, so it's a 2-2 and bent. And because of the lone pairs in the center, it's polar. PCl3 has three things bonded and one lone pair, so it's trigonal pyramidal. Again, because of the lone pair, it's polar. CF4 has four things bonded, no lone pairs, so it's tetrahedral. Because everything around the carbon is the same, it's nonpolar. BH3 has three things bonded, no lone pairs because boron is an exception. And because everything is the same, it's nonpolar. And then GS2 has to have some double bonds in there. It's fine if you use lines there as well. But it has two things bonded. And since they're the same, and there's no dots on the GE that are by themselves, it's nonpolar. This concludes our study of naming, formula writing, as well as chemical bonding.